I hope everything will be fine. So, okay, so we are talking about the method. So in our last class, we discussed about the Arduino Sao method and Arduino bond method. Okay, improvement over on Arduino bond one is system GMM, which we haven't talked about. So we'll not cover that, but in this class we will cover how to estimate. Sorry, Anderson Sao. Uh, how to estimate panel data regression model using Anderson Sao estimator and Arduino bond estimator. So let's start with the Anderson Sao uh, approach for estimating dynamic panel data regression model. So as we know, in a dynamic panel regression, we include lag of dependent variable as a regressor, and because of inclusion of that, model suffer with the endogeneity problem, and a solution of it provided by Anderson Sao is that if you use second lag of dependent variable as an instrument variable, then endogeneity problem get rid of, and we get consistent estimates of parameter. Uh, so when when we start working on the estimating the model, the challenges we face if you haven't worked with the time series regression model using Stata, that one is how to create lag of dependent variable and how to create difference of dependent and independent variable. Because our regression model for estimating the parameter would be the first difference model. And that first difference model, con- so let's do that. First, how to generate lag of variable and difference of variable. So for generating a lag of variable, I am so this one is for generating lag of variable. We just type generate, then after the variable name, or you can say a variable name, a new variable name. Let's suppose that I am typing this one is lag lag, so that we denote lag, and variable name in our case is I am choosing from the data set, which one is log of wages. So log of wage, one is our variable. I am generating lag of log of wage. So log of wage equal to, then either with L, then log of wage. So when we enter, we get a message of missing observation. To check whether lag has been generated correctly, we need to browse both log of wage variable and the variable we just have created, which one is lag of log of wage. So we can see here the log of wage variable does not have first observation value, then after eighth observation value, then after 15th of the observation value. Okay. And it is because if you see the cross-sectional ID variable, then first seventh observation belong to first cross-sectional ID. Then next seventh, second cross-sectional ID, and so on. So for each cross-sectional ID, the first period data is missing in case of lag of log of wage variable case. And since see this one is the time period, so T1, 2, 3. So first period data for each cross-sectional unit in case of lag value of log of wage variable is missing. So that means that this particular command giving us the correct result. Similarly, if you want to generate two lag of log of wage variable, so we need to type lag to log of wage equal to L2 dot LWAGE. So this gives us two lagged value of log of wage variable. The same you can see by browsing. Let's see ID and T. So let's see here in two lagged period case, first two period having a missing observation for each cross-sectional unit. So this one is the way through which we can generate lag value of any variable. So if you want to generate three lag value, so instead of uh, writing L2, we write L3 and so on. Similarly, if you want to generate difference of any variable, so this command would be the difference. So you can say for difference of so this would be the generate C D. Again, I'm generating the difference of log of wage variable LWAGE equal to, then you type D comma D dot then log of wage. So this value gives us first difference of log of wage variable. Again, we can check this one. So browse this one, log difference of wage, then L wage, ID and T. And see here, since this one is the wage data set, and this one is the difference of wage. The difference of wage is calculated here, subtracting first period log of wage value from second period log of wage value. So if we subtract 5.720, if you subtract 5.560 from 5.720, then we will get 0.159. So again we can say for a first period, data is missing for each cross-sectional unit. So again here you are having second period onward data set. this is the way for getting difference of any variable. So now we have known how to generate lag of any variable and difference of any variable. For two difference, you just need to type D2 as we have done in case of generating two period lag value. So that I am not doing, but you are not going to use that. You may experiment by yourself. So that is the case. Now let's move on to the regression model. So our regression model is in first difference form, which one is delta YIT. Let me use this stylus, which I am using for writing. I'm connecting that with the computer. I'm opening Blackboard. So, sorry, now it's called whiteboard. Our regression equation.
Sir?
Yes.
Excuse me, sir.
Yes, Bhavesh.
Sir, is this a random data set that you are using, or have you sent this data set?
You haven't sent uh, uh, the data set yet. I will send.
Okay,
Okay.
sir.
Uh,
Okay, sir.
so I'm using the Cameron Trivedi data set. So till now I haven't described the data set. We are coming on to that. Okay. So this suppose that this one is gamma 1 delta YIT minus 1 plus delta XIT plus delta epsilon IT. So, so this one is the regression model in the first difference form, and the problem of this particular regression, it suffer with the endogeneity problem, and this one is correlated with this one. So when you use OLS in this case, then we get biased and inconsistent estimates of parameter. So the one solution provided by Anderson and Hesio, one is to use a instrument variable, and they suggested using YIT minus 2 or changes in YIT minus 2 as a instrument for this variable, changes in YIT minus 1. So we are going to use this particular instrument variable in our estimation. So this one is the regression model. So now let's talk about our data set before estimating the regression model. So I'm using the data set which has been provided by Cameron and Trivedi. So Cameron and Trivedi used this particular uh, data set for explaining a Leno bound estimator. originally this data set belonged to uh, uh, and PSID wage survey, which was conducted in year 1976-82. Initially, this data set was used by Baltagi and later on by Kanti and Ecom. This data set, if you go with the description of this data set, please. So this data set contains information regarding experience, week work, occupation, which one is the dummy variable, and this takes a value 1 for blue color occupation, then industry. So again, it is a dummy variable. It takes a value 1 if worker is working in a manufacturing industry, then residence, then SA variable, which one is again a dummy variable. So if an individual live in metropolitan cities, then it takes a value 1, then marital status, whether person is male or female, whether person is uh, a member of union. Here it says if wages said to be union contract, then year of education, black, and log of wages. So this one is the standard. You think, mm, uh, and in this you are getting a data relating to the wage and the determinant of wage basically. So this the and the regression equations coming out from this data one is standard wage equation data set. So if you assume this one in a cross-sectional case or in a panel data case, so log of wage is a dependent variable and rest are independent variable. But in a dynamic setup, as we know, the lag value of dependent variable become a independent variable. So here you can say log of wage is dependent variable and lag of log of wage one is independent variable and rest are other explanatory variable. So going with the assumption that the other explanatory variable apart from lag value of wage are strongly or strictly exogenous variable. So I'm making this assumption because later you are going to realize these assumptions. Okay. So making this assumption that apart from lag value of wage, other variables are strictly exogenous variable. So in our regression equation case, all the variable that xit contains are strictly exogenous. So the only one endogenous variable that you are having, which one is the first leg of dependent variable. And dependent variable in our case is log of wage. So going with the recommendation of Anderson-Shaw, we use yit minus 2 as a instrument variable. And
Excuse me, sir, I have a question.
yes, Satadu.
Sir, what is the nature of the instrumental variable used in this case?
The nature of instrument variable is same as like what we have studied in our EDA course. So there you talked about the two conditions, strict exogeneity conditions. In that case, instrument variable not related with the error term. And the second condition one is that one is an instrument variable having a substantial correlation with the endogenous variable. So that remains, and that hold here also. I think we were not in our last class.
Sir, my question here is like you described the data set about what it contains. Sir, can you tell us like what would be the instrumental variable being used in this case?
The student variable is here in yit minus 2. Which one is the second life period of log of which? And why we are taking this? That we have already discussed in last class. For a 1 point, I am saying this one is not correlated with the changes in epsilon it here. Am I making myself clear or something else you are asking?
Yes, sir. Sir, I understood. Thank you, sir.
Okay. So, this one is the case. So we are going to estimate this particular regression, which we make here. This one is regression equation 1. So if you remember, in an instrument variable case, in a standard instrument variable case, where we run a command in which we type IV regress, you remember, then dependent variable y, then all strictly exogenous variable. Let's suppose that one is x2 to x2, x3. And if x4 one is endogenous variable, and let's suppose that z1 is suitable instrument for x1, and then after we use robust standard error. So let's suppose that we see robust. So you use this regression equation in a cross-sectional regression equation case. In a panel data case, in a case of omitted variable, so dynamic one is not a case of omitted variable, remember. In a case of omitted variable, we just need to prefix IV regress with the XT IV regress. Then the whole equation comes and then fix effect. But since this one is a dynamic regression equation, so the command of dynamic regression equation is same as we use in case of omitted variable. So we type xt, since again, sorry, it's a difference because here you are using a regression equation in label. So this one is the first, though you are using a fixed effect, but here you are using a x1, x2, x3, and then x4 is a omitted variable. And because, sorry, x5 is a omitted variable, and since x5 is correlated with x4, so x4 become endogenous. So, and instrument of that endogenous variable is x4. So you use FE options, okay, to estimate panel data regression equation in case of omitted variable. In a dynamic case, since we do not use regression in label form, instead of using a regression of label form, what we use? You use regression in first difference form. So this one is the first difference regression equation. So accordingly, you type here. So you use XTIV regress, XTIV regress. Then y is here in first difference form. So we may type here dy. Then after all exogenous variable, again in a first difference form. So dx2, dx3, then dependent variable. Let's suppose that if x4 one is the dependent variable, this one is the endogenous variable in our case. So this become d L dot y equal to this one is the instrument variable. So what we type here? L y L2 dot y and then fix effect. Are you getting me? Hello, are you getting me? Or shall I explain it again with a new equation?
Sir,
Yes.
sir, what was the DL part where we use DL?
Okay. I'm coming on to that. Let me start again. So this one is the regression equation. Gamma 1 del y I t minus 1 plus del x I t beta plus del epsilon I t, and instrument variable of y I t 1 is y I t minus 2. Is it clear to you,
Yes,
to
sir.
everybody? Okay, now I'm going to incorporate this one into our regression equation. So for this, okay, so this one is the delta yt. Okay. So we write d, which one d represent difference here, and then y. Since you are working with the the panel data set, so there is no need to write it. Simply y, dy. This one, this I'm talking about. This one we write in a form of d l y. Why dly? Because y is the dependent variable. When we type ly, this gives you us a first leg value of dependent variable. And when we prefix with d dot l dot y, so this gives us del y t minus 1, which one is y I t minus 2 minus y I t minus 1. Okay.
Yes, sir.
So because of this region, when we type command, we type xt I v r e g, which one is xt instrument variable regression. Then this one is the dependent variable dy d dot y, of course. Then all explanatory variable first. So which comes as, since let's suppose that there are only two explanatory variable and both are continuous variable. Okay. So we type dx2 dx3, then we bring this one endogenous variable. Which one is here? D L y, and instrument of this endogenous variable one is L2 y. L2y give us this value. So when you type L2 dot y, this gives us y I t minus 2. So this one is the second leg of dependent variable, and then fixed effect. And when we type this command into our regression equation, this gives us Anderson and Shaw estimates of parameters. So let's use this one. So assuming that this one is our correct regression equation model. So what we type here we type d dot log of which one is dependent variable, then d dot, if you want to include year of education, let's suppose that So year of education, and let's include one more variable. Which one is would be again continuous variable? This one, WKS. I'm including only two variables, but this one is just an illustrative exercise. We are not working with the correct model actually. So these two independent variables. Then after, in bracket we type endogenous variable. Which one is first leg difference of first leg of dependent variable. Which one is? This one is the first difference of first leg of dependent variable. Which one is? D dot L dot ln which equal to instrument variable. Which one is? L2 dot ln which, and then FE. Which one is the option for fixed effect, and enter this take is a D dot L which invalid command name. Oh, sorry. I haven't typed this
Instead
one.
of LN wage, it should be L wage, I guess. Right?
No. Oh, okay. One mistake we made here. So this should be L wage. I define log of wage as ln wage. So one is in my mind by default. So one more, we haven't typed command. Which one is xt ib regress, and enter. So this gives us which we call Anderson-Shaw test statistics. So Anderson-Shaw estimates of fixed effect model. So within R square, you are getting here as a dot. That means that is not defined by this particular model in this with this particular data set. It is probably a constant variable or dummy variable. That's why you are getting estimate 0. And these are the results. The result is same as like what we get in case of fixed effect model.
Sir, can you
So
show
this
the command again for a second?
this one is the command. So the important thing is that we always try to observe that one is in for number of groups. So the number of groups must be larger than the number of period. Always remember, because you are working with the that one is the condition of working with the short panel data set. So group is 595 here. 5 is the time period. We are getting here 5 because 2 time period is omitted from our data set while estimating this particular regression equation, because you have used 2 lagged value of dependent variable. So the time period is starting here from t equal to 3. This one is the Wald chi-square having as usual interpretation. This one is the correlation matrix of error term and dependent variable. So correlation is here. The correlation between the error term and independent variable is here 0.003, which is showing almost no correlation between error term and explanatory variable. And this one is the as usual standard error of unobserved error term and idiosyncratic error term. This one is the variation. And fraction in variation of error term due to UI. And instrument is here, which one is the difference of WKS variable and second lag value of log of wedge variable. So this we know that this one we incorporated as an instrument of changes in first leg of difference variable. In our data set, we have considered WKS variable as a strictly exogenous variable. So when you use instrument variable, all strictly exogenous variable are instrument for themselves. So that's why WKS variable become instrument for itself. And so that's one. So, so this is the command for getting Anderson-Shaw estimates of parameter. Now let's move on to the Arlino-Bond estimator. So, in a case of in a Arlino-Bond estimator, you use different instruments for different time period. And if you remember, let me open that. So this one. So Arlino-Bond define instrument as like this. So for t equal to 2 and t equal to 1, there is no instrument. But beyond that time period, so for t equal to 3, instrument variable is yi2. For 4, it is yi2 and yi1. For 5, it is yi3, yi2 and yi1 and so on. So let's suppose that in our data case, we are having t up to 7-year of time period. So starting with the 1 to 7, and cross sectional you are having, as just you have seen. So if I type code book ID, so cross sectional ID you are having 595. And if you see this particular slides, then it says that for defining an instrument for y for delta y I t minus 1, which one is our endogenous variable, we get instrument for a period 3 onward. And that means if you're for a third period, we will have one instrument. For a fourth period, we are having a 2 instrument, fifth 3 instrument, and sixth 4 instrument. So total is and for seventh 5 instrument. So the total instrument variable that we can use and at a maximum number or in a maximum number. So maximum number of instruments in this case would be 7 plus 5 plus 7 plus 6 plus 5 plus 4. Sorry, make a mistake. 1 is for 3, 2 is for 4. So 1 plus 2 3. 3 is for 5th. So 3 3 6. 4 is for 6th period. So 6 plus 4 10. And fifth one is for 7th period. So 15 instruments for a one endogenous variable. I am talking about for a one endogenous. I am emphasizing this one because you are going to talk about this when we actually estimate our model. So let's do that. And for doing that, we are going to stick with the current data set, but we are going to modify our model a bit. So in our earlier model, we have included only one lag value of dependent variable as explanatory variable. Now I'm going to add another lag value of dependent variable as a explanatory variable. So the structural regression equation in this case become yit gamma 1 yit minus 1 plus gamma 2 yit minus 2 plus, let's suppose that matrix sum all explanatory variable plus alpha I, which one is unobserved cross-sectional heterogeneity constant over period of time, plus epsilon it. So this one. Taking a first difference, this become delta yit, this one become delta yit minus 1, this become delta yit minus 2, this become delta xit beta, this one vanished out, and this one become delta epsilon it. So this one is first difference regression equation. And you are going to estimate this one. I am using this because this particular equation is given in Cameron and Trivedi microeconometric research data book. Okay. And we will find each and everything what I am going to discuss now onward. Whatever I have discussed till now, probably that we do not found in that book. For that, we may have to refer the different papers. Or if you go through the entire chapter of chapter 9 from microeconometric risk data, in where authors talked about using instrument variable in a omitted variable case. So after then, probably we'll have a better understanding of these Anderson Chow estimators. Okay. But this thing, this one, since I'm exactly using the equation given in the textbook, I'm going to discuss, and whatever I'm going to discuss that also given in the book. So you may have a direct reference of the book only. So this one is the regression equation. Now we require instrument for these two endogenous variables. let's again, if you are assuming that this one is strictly exogenous variable, so you require an instrument for these two. And the way we construct our instruments based on this particular slides. So what I am going to do, I'm directly going to estimate the regression equation using Arlino bond estimator, and after then we see how the instrument variable has been constructed by Stata, and then we and taking number of instrument variable used by Stata, we try to figure out the way of constructing instrument variable. So for that, I am using this particular command which we call xt a bond, which is Arlino bond, then log of wage, not going to include any explanatory variable just for a simplicity or making the things more simple. So lag 2, then VCE robust. So VCE robust option to get robust standard error. Lag 2 option, as we have used 2 lag of dependent variable as an explanatory variable. This particular regression command has not included any other explanatory variable. So only dependent variable or lag value of dependent variable is explanatory variable here, and explanatory variable are here 2 lag value of dependent variables, yi t minus 1 and yi t minus 1. So let's enter. So when we enter, we get this particular estimate which called Arlino bond one steps estimator, and see here log of which is dependent variable and lag value of log of which and 2 lag value of log of which are independent variable. Both are statistically significant. See the number of group 595, time period is 4 because 3 time period having a missing observation, you can say, since the regression equation that is estimated in this case one is in first difference form. So when we take a first difference of yit minus 2, okay, so that one is yit minus 2 minus yi3 minus yit minus 3. So 3 time period is omitted in calculation of that regression equation model. So that's why you are having only 4 time period, 4, 5, 6, 7. Chi-square value is again statistically significant. Now let's move on to the bottom part of this result, which one is uh, uh, deals with the instrument for difference equation. So the method is GMM method. Then after it's written here L2 oblique dot LH. So while constructing instruments, okay, this particular option suggests us This particular model has used 15 instruments. Look here, number of instruments given in the top, and that instruments one is y I t minus 2 onward. So in this case, $15 instruments become something like for t equal to 4 time period. There are 2 instruments. Let's again go on to this slide. So for t equal to 2, so when t equal to 4, only 2 instruments is possible. Which one is yi2 and yi1. For t equal to 5, 3 instrument is possible, yi3, yi2 and yi1. And so on. So for t equal to 4, 2 instrument, t equal to 5, 3 instrument, t equal to 6, 4 instrument, and t equal to 7, 5 instrument. So total become 14 instrument. 2 plus 3 plus 4 plus 5, and 1 instrument is intercept, which become instrument for itself, or 1 instrument for constant, or whatever you can say. So the total instruments used by this particular model is 15. So that's why you are having here a 15 instruments. These are the coefficient value 0.57 and 0.26. That mean,
Sir, could you just repeat the last thing that you said, sir? I think my connection was cut off.
okay, we are talking about the number of instruments, and when we refer this slide, so here it talked about for t equal to 4, we get 2 instruments, yi2, yi1. So 2 instrument for 4th time period, 3 instrument for 5th time period, 4 instrument for 6th time period, and 5 instrument for 7th time period. So when you add all these instruments, it become 14. And 1 instrument, which one is one instrument coming out from constant term, which become instrument for itself. So total instrument value is 15. So total number of instrument is 15. Now looks on the coefficient value of lagged of log of wedge value. So here it is 0.7, first log of wedge coefficient. The first lagged of log of wedge coefficient is 0.57, and second lagged of log of wedge coefficient is 0.26. So here you can, for interpreting the first lag value of log of wedge coefficient, you can say if 50%, 0.57% of log of 5.57% is the previous year affecting the current year. So more than half of the wage of current year period, you can say the explained by the past year wage data. So we and if you get the total, so it's become a 0.57%. 0.84. So that means we can say here the wage depend upon the past wages with a lagged weightage of 0.7 for first period and 0.27 for the second period. In terms of increases in
Sir, we can't hear you. Sir, I think
no,
there is.
I'm
Yeah, you were not
I'm saying,
audible.
am I audible now?
Yes, sir.
Okay. So this one is, we can say, the weightage of previous year wage effects on current year wage. So that also, though even I'm not very much sure how far my interpretation is correct. Okay, but you can say that 57% of uh, current wage is determined by the previous year wage value, and just immediate previous year wage value, and 26% of current wage value is determined by the previous to previous year wage value. So something like this. Okay.
So,
Of course, yes.
since we are using log of wage instead of wage, so can we straight away say about the wage variable, or should we interpret in terms of log of wage?
We should interpret in terms of percentage.
No, sir, I'm saying in terms of log of wage because
Up,
it
yeah,
is different.
we can interpret in terms of log of wage. Okay,
Yes.
definitely. Uh, mhm, no, no, I'm getting it. Now I'm getting it. We are saying that since I am using the interpretation in terms of wage, so we are saying that we should interpret in terms of log of wage.
Yes, sir.
That's what do you mean? No, we interpret in terms of wage only, because one is just a transformation of another. Okay, so if I say 57% of current wage value, since I'm using a percentage here, okay, so 57% of current wage value is determined by the immediate previous year wage value. So, it seems correct because I'm using the percentage in our interpretation. In a cross-sectional data set, in a log-log regression equation model, we say that when wage rise by, and let's suppose we are measuring in terms of experience. So we can say not in experience. Experience we can't measure in a percentage. But wage, or let's suppose that there is a one x variable that that is measurable in percentage. So you can say when x rise by 1%, on average y rise by 0.57%. That was the interpretation. And in case of log-log model, in a cross-sectional data case, so similarly you can interpret here also. So 57%, 0.57%, I'm that what, okay, this one is the previous year wage value. So we may say that previous year wage value rise by 1% on average, current year wage value rise by 0.57%.
Okay, sir.
Okay. But again, I am saying, since I haven't worked with such kind of model yet, okay, when I am dealing with this particular type of the model. So for appropriate interpretations, be better if you refer some empirical example. Because even in a Cameron and Trivedi book, they haven't interpreted the result. They just said that wage depend greatly on past wage with a lagged weight of 0.57 and 0.27. So instead of saying this, because this one is with general interpretation, but it might be instead of this, it would be something like this: the previous year, immediate previous year wage rise by 1% across cross-sectional unit over a period of time. Then on average, current year wage value rise by 0.57%. So, but this interpretation comes with a rider, because since I haven't gone through the empirical literature, okay, so it would be better to first go with the empirical literature and then interpret the result, so that the interpretation should be more appropriate. Okay, so if you find a correct any interpretation, okay, either that match with my interpretation or not, just let me know about that, so that we all of us know the correct interpretation.
Sir,
Okay, sir.
Yes.
sir, before moving forward, can you show us the command again?
The command is given in Cameron and Trivedi book. I am this, and now onward I am using Cameron and Trivedi commands only.
Okay, thank you.
So we'll find all these command in the book. Even
Which chapter is this, sir?
this one is chapter 9, section 9.4.4. So
Sir,
yes,
sir, also there were two books for Cameron and Trivedi. One was Microeconometrics using Stata, and second one is Methods and Applications.
the today's session one is from the first one, microeconometrics using Stata.
Okay, sir.
So all our practical sessions for a panel data regression model from this book only, microeconometrics using Stata. For a theory, a little bit portion of microeconometrics method and application I have used. For theory, this time I have used Woodridge book. So you have to go through the Woodridge chapters for going through the theory, and for empirical things is given in a Cameron and Trivedi, both for basic and panel data regression model. For basic, my on PPT is sufficient. We may complement that with the Princeton University document, which I told you to download from the Google. So that much is, I think, enough, along with my video lecture. Okay, even if you do not go with my video lecture and just practice by yourself using the PPT provided by me and PPT that we get from the Princeton University, that will be sufficient. For a panel, I think we need to read more. All the practical things we will get from the Cameron and Trivedi, apart from the Anderson Shaw things. So this one is in case of one estimate and one step estimate in case of Arlino bond estimator. Since it is already 3:45, so would be better if we stop here. In the next class, we'll do rest of the things, and after then we start with the logit and profit regression model. So next class would be Saturday, but probably I will not take your lecture on Saturday, but I will inform about that a day before of that. That one is on Friday. Okay. So I'm going to stop this recording. So any doubt, any other doubt?